Okay, we're going to work on converting decimal to binary. So we talked a little about this last time. Binary is a number system that has only two digits, right? We have a 0 and a 1, and that's it. We'll call this B for binary. In the decimal system, we have 10 digits, starting at 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's 10 different digits, right? And we just switch between those digits unit places. So think of them like as the place value. Here there's only a one place value all the way down. In the binary there's only one. Now we could create a chart here. How do I represent 0 in binary? When I say 0, I'm referring to the decimal numbers. Please do that later. Thank you. Probably everyone saw that password. Wonderful. Have to change that now. We have 0 and 1. And then how do I represent 2? Well, I go 1, 0. Okay? How do I represent 3? I go 1, 1, which looks like 11 to us, but what it's doing is it's just exhausting all the values in that place value, and there's only two values. How do we do 4? Well, we'd go 1, 0, 0. And then 5, we'd go to the first place value, 0, 1. 6 would be 1, 1, 0. 7 is 1, 1, 1. 8 is 1, 0, 0, 0. And 9 is 1, 0, 0, 1. Great. Except that, what if I want to figure out what from decimal 63 to is in binary? I would have to continue this chart, and it would take me a really long time to do this. A simpler way to do this is if you have larger values, is we do this mechanism or this process of dividing the value by the new base of the number system. So when I say decimal, that means this is a base 10, okay? Base 10 number system. When we say binary, that is a base 2. So I take 63 and we divide by 2, okay? When we divide, we have to pay attention to the remainder and what the quotient or the answer is every single time. So 2 into 63 goes in 3 times, okay? And then we have a 6, we subtract the 0, bring down the 3. 2 goes into 3 once, we have 2, we subtract, we have a 1. The remainder is 1, wonderful, okay? I'm gonna write my binary answer down here. That remainder is the first digit in my binary answer, starting from the right going to the left. I then take the quotient, that becomes my new answer. Am I saying that right? Is that the quotient? No, quotient is what you divide into. What is this? Product sum quotient. Oh my god, I can't remember that term. I'll figure it out. We take that new answer, we divide it by 2, and we repeat the same process. And every time the remainder is one of the binary digits. Okay. So 2 goes into 31. We can do the long division. Do you know what it is off the top of your head? Okay, we'll do the long division, and I'll show you kind of a shortcut for this after. 2 goes into 3 one time, so we put our 2, we subtract, bring down the 1. 2 goes into 11 5 times, that is 10. Subtract, get 1. There we go, 1 is the remainder. We put our next binary digit, and then we go into 2 goes into 15. Okay, 2 goes into 15. Another fast way to do this is knowing your 2 times tables really well, and we just find out the product of 2 multiplied by a number that's less. Yes, 2 times 7 is 14. Wonderful. Remainder 1, we get it again. And we're going to continue. 2 goes into 7. 3 times. Remainder 1. Okay. 2 goes into 3. 1 time. Remainder 1. And then 2 goes into 1. 0 times. But what is our remainder? Still 1. Okay, so we have, I'm going to count them across here, backwards kind of, 1, 2, 3, 4, 5, 6 place values, okay? So 6 place values, this is our binary digit that represents 63. So if I shrink this a little, nicely, we can test this. Each of the place values in binary, 1, 2, 3, 4, 5, 6, we said there's 6 place values. Think of it as representing the base, so it's base 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and 2 to the power of 5. Each of those we can get a value for. I'm going to write them just below. 2 to the power of 0 is 1, 2 to the power of 2 is 2, 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. We're just going to keep doubling. 8, 16, 32. Okay? So, if there is a 1 in this place, think of it like there's the number 1. So if we do 1 and 1, let's say that was your binary value. Think of it like taking 2 and adding 1. What's 2 plus 1?
3.
Hey, look at here. 3 is represented by 1, 1. Okay? If I have another value here, that's 1 plus 2 plus 4. What does that add up to?
7.
7. What is 3 binary digits? 7. Okay? So it's working out great. So apparently, all of these equal to 63. Well, we can just add up all these values to find that out. So 32 and 16 and 8 and 4 and 2 and 1. I'm going to show you a really cool adding trick. Always try to make tens. Okay? So I'm going to go 2 and 8 is 10. 6 and 4 is 10.
63.
Ah, very good. We get 23 here. We add a 2. 2 and 3 is 5. Boom, 6. 63, was that our decimal value? Great. So not only do we convert from decimal to binary, but we kind of figured out how we can take a binary value and bring it back to a decimal value. Okay? Does that make sense? So let's do one more value. I'll shrink this a little more. Yeah. Because binary is base 2, we always divide by that base. So let's try another digit. I'm going to try something a little smaller, but hopefully I'll have some zeros. Let's try 25. I'm going to try 25, okay? So 2, we divide by 2 because binary is base 2. There's a 0 and a 1. So 2 goes into 25 12 times and has a remainder of 1. So I know that we have a 1 value. 2 goes into 12 6 times. There's no remainder, so that becomes a 0 value. Okay, so this is where it gets important. 2 goes into 6 3 times, no remainder. 2 goes into 3 1 time, 1 remainder, and 2 goes into 1 0 times, but 1 remainder. So this is our binary digit according to what we said before. Remember, we said it's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and each of those are equal to 1, 2, 4, 8, and 16. So we have a 1 here, a 1 here, and a 1 here. So we can add these values. 16 and 8.
24.
24. Plus 1.
25.
Did we get it?
Yep.
We got it. 25.